Hello and thank you for joining us today. My name is Amanda Sturkenberg and I'm the Content Manager here at Regenesis in Europe. Before we get started, I have a few admin items to cover first. We'll try to keep this webinar under an hour, and at the end of the webinar there will be a question and answer session. Now, if the webinar or audio quality cuts out or degrades, please try refreshing your browser first. If that doesn't fix the issue, then please disconnect and repeat the original login steps to rejoin the webinar. If you have a question, we encourage you to ask it using the questions or chat interface provided on your webinar panel. I'll collect all the questions and we'll do our best to answer them at the end of the presentation. If we do not address your question, we will follow up with you after the webinar via email. We are recording this webinar, and a link to the recording will be emailed to you once it is available. Now, in order to continue to sponsor events that are hopefully of value and worthy of your time, we'll be sending out a brief survey following the webinar to get your feedback. Before we get started with today's webinar, I'd like to introduce our guest speakers, starting with Jack Sheldon, Senior Consultant at Antea Group. Jack leads the firm's site assessment and remediation service line in the US. He has over 40 years of experience in environmental microbiology and remediation. He has a BS in bacteriology and public health and an MS in environmental industrial microbiology from the Wagner College in Staten Island, New York. In his current role, he advises on remediation, technology selection, performance and optimization across the US and abroad. He has authored numerous papers and posters, co-authored 2 best-selling books on bioremediation, and given hundreds of presentations and webinars around the world on remediation technologies. Our second presenter today is Dora Taggart, President and CEO of Microbial Insights. Since joining the firm in 2001, Dora has advanced the field of molecular biological tools, including pioneering work in qPCR analysis and stable isotope probing. She continues to collaborate with leading researchers in academia and US federal agencies, and as a CEO, she has become a global ambassador for molecular biological tools, regularly presenting as an invited speaker at environmental and corrosion conferences, leading technical workshops, and co-authoring guidance documents. She's received her degree in biomedical engineering from the Vanderbilt University. Okay, and with these introductions complete, I will now hand you over to Dora to get us started.
Wonderful. Thank you so much, Amanda, for that kind introduction. It's really an honor to be here, and I think the talk that Jack and I are going to do today will be very valuable, and it's going to be particularly focused on petroleum hydrocarbons. But this really excites me a lot because we know the good science that goes behind the products that Regenesis uses in site remediation, and then working with Antea and the good field practices and the precision bioremediation that they apply on a regular basis is going to be the focus of my talk. So I'm really honored to be able to be here and to participate. So let me start by saying what I mean when I say precision bioremediation. So to me, this is a refined approach where we're using microbes to help us clean up contaminated sites, where we move beyond just using traditional methods to incorporating advanced biological characterization. And this gives us a way, using these interdisciplinary approaches, looking at multiple lines of evidence, understanding these key microbes that are present, so that we can optimize our overall performance at a site, and therefore that's going to reduce the overall cost that's associated. So how do we do this? We do this by identifying the specific microbial communities that are present. So then we can start to understand their metabolic capabilities and then tailor the remediation strategies to maximize their effectiveness. And that's what Jack is going to show you today in the case studies that he presents. And it all starts with good basic science. There's good science that goes into the products that are developed and how they're used and implemented in the sites. But there's also been a really long period of investment into good basic science in petroleum hydrocarbon degradation. So this is a textbook image that you've probably seen of a site impacted with petroleum hydrocarbons. And what's important that I want to point out is that near the source area, electron acceptors really become depleted very quickly as a lot of electron donor from the hydrocarbons that are introduced into the environment really creates this selective pressure of what's going to happen in that environment. Then as we move down gradient, we typically see an increase in the availability of electron acceptors, with the toe of the plume often being nitrate reducing, aerobic, or sometimes microaerophilic conditions. And this is important because in each of these areas, there's going to be different pathways, different microbial activity that's going to affect and enhance that biodegradation process. The good news is there are typically microorganisms that are present in our sites that can help us degrade the contaminants of concern. But the important point that we have to address and why we need to understand these microbes is we need to answer the questions, do we have enough microbes that are present? And do we have enough of their metabolic requirements that they can survive and perform the processes that we're interested in seeing? As I showed in that last slide, this can be difficult as the hydrocarbons that are released provide so much donor for the microbes that the other side of the process can become limited very quickly. This will cause a selective pressure where only certain groups of microorganisms can survive. And an example of this would be a site that has a lot of aerobic potential initially. Once the hydrocarbon is introduced, tends to move to sulfate reducing very quickly. So then you'll stimulate different pathways like those of sulfate reducing bacteria that are present. So historically, we've struggled to understand what the microbes are actually doing because we see it as like a black box of what's happening in the subsurface. We know what was going on in the site itself. We know what products are coming out after we've done some type of biostimulation or enhancement, but we didn't know what the microbes were doing in the middle. So the good news is with the microbial revolution that's happened over the last 2 decades, we really have a much better way that we can track and document these organisms. And then engineers like Jack can go in and harness their power so that he can be much more effective in the remediation practices that are applied. You know, back in the 80s and 90s, we tried to grow these organisms on plates. We found that to be not very effective because less than 1% of organisms like to grow. But with the advancements in DNA-based technologies, we've moved very quickly to be able to quantify organisms, groups of organisms and genes that we're interested in, and even start to do more site assessment in the field. So today I'm going to focus on a technology called QuantArray that you may be familiar with, and Jack's going to show you in his case study some information on that. So my goal is to kind of introduce the tools to you, show you a really quick case study, and then Jack will dive in much deeper into the data. And I just want to reaffirm that for precision remediation to occur, including the microbiology is really an important line in the site assessment. And I think you're going to see that in these case studies because a multiple lines of evidence approach is what gives us the ability to make these really good decisions and ultimately to be precise in how we apply the products and the services that we have. So by incorporating an understanding of the microbes that are present, the environment can be manipulated so that we can enhance the activity of these naturally occurring microbes. And then knowing how these microbes are surviving or thriving in all these different areas of the plume and the source area compared to the toe of the plume, that provides information so we can go in and be very targeted in our assessment. Rarely, as Jack is going to show you, is one process occurring. However, we can start to understand these various processes and begin to harness and control that power much better. And this offers the potential for more effective and efficient contaminant removal. It reduces the remediation timelines that happen and lowers the overall cost. So how do we look at the microbes? The first thing we need to think about is where to collect our samples. So the source area, as I mentioned, usually is very different from the down gradient location. So getting a sample in this area is important. And then also, especially for petroleum hydrocarbons, looking at where concentrations of contaminant change because we'll have varying electron acceptors that will be available. So those down gradient locations, and then comparing that to a background location can often be very helpful. At large sites, there may be some periphery areas that you're interested in that you want to take a look at, or a down gradient because of receptors that might be important. And typically, for those of you that aren't as familiar with this technology, we're going to do a lot of analysis of groundwater samples because those are easy to collect. And so this is something that we can do in the field where the groundwater can be collected with field pumping methods. Those field filters are sent into the lab for analysis, but also if we're installing wells, we can look at soil samples or other technologies that are available to collect those microbial populations. So this is what the field filters look like. You just collect up to a liter through the filter, send that to the lab for analysis, and then you'll get your data back from these samples. So let's talk about petroleum hydrocarbons in particular. As I mentioned in the beginning, there's a lot of research that's been done into the pathways for petroleum hydrocarbon degradation. So for you take toluene, for example, we know 5 aerobic pathways and at least 1 anaerobic pathway for degradation of this compound. And typically at sites, it's not just toluene or just benzene that's present. There's going to be mixtures of compounds. So that's going to mean that we have a lot of different pathways that are of interest for us to be able to evaluate and to see how they look in that source area compared to those down gradient locations. So many of you have probably heard of qPCR. That really became a household name during the pandemic, and we saw that it was an accurate way that we could quantify organisms or genes that we're interested in. So a technology that Jack is going to show you in his case studies today is something called a quantarray, which is where we collect a groundwater or a soil sample from a site location, extract the DNA, and then we run those different genes, whether it's aerobic degradation genes for the different compounds of interest or anaerobic genes. We know all of that information in a single analysis, which can be very powerful for us in the interpretation, as you're going to see in these case studies today. So here are a list of some of the genes that are used. And I think the important point for you to understand is that although there are a lot of genes, there's redundancy that Mother Nature has built in. So there's a lot of genes that can give us good aerobic degradation of BTEX and MTBE, aerobic degradation of PAHs and alkanes that may be present at a site. There are also genes for anaerobic degradation that we understand, and more research that's being done to elucidate more of these mechanisms. But right now we know 3 different anaerobic genes that are important for anaerobic BTEX degradation. We know several genes for anaerobic PAHs and alkanes, and as I mentioned, we're learning more all the time. So these genes can really give us information on what types of processes are likely dominant in certain areas of the site. And when we add different compounds of interest, then we can see how those organisms are responding, how they're growing. So if we add a colloidal activated carbon to the site, we can see how we're stimulating the microbial populations that may be present in different areas across that location. Another tool that Jack is going to show you today in the case studies is something called stable isotope probing. And this is probably my favorite tool of all because it's a very direct, definitive answer that you can get. And it's a way that we couple molecular techniques with stable isotope compounds to prove that degradation is happening of a particular compound of interest under our site conditions. And then we can link that biodegradation, again, precision remediation happening, to the responsible organisms that are present in that site. So for those of you that haven't used this tool before, I just want to give you a quick example of how this works. So in the environment, we know that 99% of our carbon is a 12 carbon molecule, 1% is 13 carbon. So if we flip the ratio for a benzene like you see here, and we make that benzene that's 99% 13 carbon, we can use that heavy weighted carbon as a tracer in contaminant degradation. So looking for it in the microorganisms or into carbon dioxide and using that as tracers to understand the fate of our contaminant. So it's definitive proof that our compounds are biodegrading. So the way that it works is we take a 13 carbon compound, load it onto something called a biosep bead that I'll show you quickly in a moment. These go into biotrap samplers that are deployed into the monitoring well for 30 to 60 days. There are no microbes that are present on these biotraps, so the native microorganisms that are present at your site are going to colonize these beads and form biofilms on them. And because organisms like to be present in biofilms, you're going to see growth of microorganisms that happen inside these beads. And then those that are able to use the 13 carbon benzene, for example, will start to biodegrade that, and they'll make more biomass, or they'll make carbon dioxide. So then we can look for that 13 carbon, that heavy weighted carbon, into both the biomass of the microorganisms and into that carbon dioxide at the site. So this is done through something called a biotrap sampler that's made of powdered activated carbon and Nomex. This is a patented technology that was developed by the University of Tulsa and DuPont, and we've been using it for almost 25 years now in site assessment. And so this activated carbon gives us a way to absorb the compounds that we're interested in, just like very similarly to what you're going to hear with the CAC that we're going to talk about today. And so then the microbes can colonize, they'll grow there, they'll start to use those compounds because they're still bioavailable to those microorganisms. So we know how much of a 13 carbon benzene we put onto these biotraps. We can see how much we lost during that deployment period. And then we can know that we had a relative rate of loss that occurred. But more importantly, we can look for that heavy weighted carbon into that carbon dioxide as the organisms mineralize that compound for energy, or we can look for it into the bacterial biomass as they metabolize it and grow more cells. So I want to show you just a really quick case study here that I think is a good representation of both of these concepts. And I'll give you a quick introduction before I turn it over to Jack to take it further. So this is a site that was in a shallow groundwater aquifer. It was a manufactured gas plant that had been in operation for a very long time. And they had done source area excavation, but they still had some residual naphtha that was present. And in particular, they were concerned about benzene, naphthalene, and methyl naphthalene. And what they wanted to understand is, do we have enough microorganisms that are present at the site that are degrading the compounds, or are we going to have to do a lot of active treatment? And if we do active treatment, what is going to be very effective for us? So those are the questions that they had moving into it, again, trying to be precise in the bioremediation approach. So this is some data from our QuantArray Petro, and this is focused on the PAHs to show you that first. There were 3 wells that were analyzed in this particular case study. 1, 17D, is our background location. 7C is our source area location. And UMW 44 is a down gradient location. And as you can see from the groups of organisms that are detected, on the left you have aerobic genes for degradation of PAHs. So we have some naphthalene genes that are present that can degrade naphthalene aerobically in both the source area and down gradient. And then look at our anaerobic degradation genes for PAHs on the right side of that graph there. Those 3 genes are very high abundance present in the down gradient location in particular. And those percents that you see at the top, the 63rd, greater than 96th, and 93rd percentiles, this is from the database that Microbial Insights keeps of all the different genes that we've analyzed. We have over 250,000 samples from sites all over the world. So if we look at this and we say, what does that concentration mean for anaerobic degradation of methyl naphthalene or anaerobic degradation of naphthalene? You can see we're in the top 10% of sites around the world for that degradation ability. So when the contaminant reaches that down gradient location, there are a lot of microorganisms that have the potential to be able to do this degradation. Also on the BTEC side of things, there were 3 monitoring wells, again, a background, a source area, and a down gradient location that were selected. And what you can see on the left side of the graph, we have aerobic BTEX degrading genes that are present that are capable. So you have a lot of redundancy, low concentration. So even if microaerophilic amounts of oxygen come through that system, these organisms have the genetic potential to be able to degrade very quickly the BTEX that's present. Down gradient, we see some genes for anaerobic BTEX degradation that are being detected as well. So what does this tell us when we're looking at site assessment? Again, for precision remediation, we really want to take that multiple lines of evidence approach so that we can be sure we're creating actionable data that can be meaningful for us in the site assessment. So if we look at the chemistry of the site, we knew that the contaminant concentrations were stable or decreasing from a Mann-Kendall trend analysis. The electron acceptors were being consumed across the site, so there was microbial activity that happened. And then by adding this third line of evidence, looking at that microbiology, we can understand that there are very high concentrations of organisms, particularly in that down gradient location of the plume, that can degrade the naphthalene and methylnaphthalene as it flows through the site. So I was lucky enough on this to be part of a regulatory review panel that reviewed the data for this location. And the regulatory agency had a really good question, and that was, we can see that the organisms are there and the genetic potential is present, but how do we know for sure that the contaminant is going to biodegrade today? So the next thing that we did is the stable isotope probing analysis at a few locations. In particular, these compounds, we wanted to look at benzene and naphthalene. And so some biotrap samplers were deployed in a couple of locations across the site. UMW 44 and 7C were of interest for the naphthalene and methylnaphthalene that's present. So there was a 13 carbon naphthalene biotrap that was put in each location. And then monitoring well 6E had a benzene biotrap that was deployed. So you can see the site groundwater contamination levels that are there at the current time. And then just to quickly get to this, because I want to turn this over for Jack to show you some more in-depth information, this is the data that you would see from doing this type of analysis. So when we do stable isotope probing, we're looking at the ratio of 13 carbon to 12 carbon, and that's going to tell us how much of our compound was biodegraded. So in nature, this delta value, that's our 13 to 12 carbon ratio, is typically going to be very negative. For carbon dioxide, you're going to have a minus 25-ish value. For phospholipid fatty acids, which is the bacterial biomass, you're going to have around a minus 20 to minus 25. Well, you can see here in these two figures, if you look at the blue bar on the left-hand side, our dissolved inorganic carbon is positive 50, and our monitoring well 6E, so that's definitive proof that the 13 carbon benzene on the trap was mineralized by the microorganisms. Carbon dioxide was made from that heavy weighted carbon. On the right side, you can see the biomass incorporation, and you can see that it were around a positive 30. And this is, again, definitive proof that the benzene was utilized by the microorganisms to make new biomass. So there's no way this could happen in nature unless benzene was being biodegraded to get this much of a positive number from either of these biomarkers. The same thing for naphthalene. You can see here we have a positive almost 250 in our carbon dioxide on the left-hand side with that blue bar, and we have a positive 850 in our biomass in this monitoring well 7C. We also had another well with naphthalene that we saw the similar type of trend that happened. So across the site, not only could we say that the microorganisms were present, but with the combination of these analysis, with the combination of this multiple lines of evidence of looking at the chemistry and the biochemistry of the site, we were able to infer that not only were the organisms there, but they were actively degrading those compounds of interest. So that gave us conclusive evidence that the bioremediation was occurring. And this is a great tool that if you're adding an electron acceptor into the environment and you want to see how that responds, you can do a pre and post to look at the level of incorporation that we're seeing into these, and it's a great way to prove that these compounds are working so effectively. And we do this a lot with Regenesis on sites, and I think it's a really valuable tool for you guys to use. So as I wrap up today and turn this over to Jack, I just want to briefly mention that, it's our goal at Microbial Insights to help with precision bioremediation and to offer these tools to work with great industry partners and academic partners to better understand what is happening in site assessment. And we're not owned by a consulting firm. We don't sell any products or cultures, but we work closely with companies like Regenesis who have the cultures, who have the different products that are available. And so we can help you show that these products are really effective. And I see that in the science that goes behind the development of the products. And it's great to see it in practical application all over the world. So after doing this for nearly 25 years, seen a lot of different sites. And I think the components that are being sold now, the ways that we are applying these amendments are really valuable in site assessment. And so I would encourage you to think about precision remediation because I think overall it's a great way to have a cost savings in your total site assessment. I know that not everyone gets as excited and geeked out about thinking about microbes as I do. So I'm happy to always be a resource for people. If you have questions that you would like to pass by, I'm always happy to be part of the team and help you understand what that data means. It's always a pleasure to talk to Jack and to be able to look at sites and see how we're generating actionable data in our site assessment. And I would encourage you to use the resources that are available to you because there's a lot of great publications now. There's a lot of good information. The database can add some context to the values. And so you're not on your own trying to interpret this data. There's a lot of great people in the industry that can help. So we are doing this all over the world. It's a very exciting time. We are based in the United States, but we're seeing countries all over the world, more than I think 60 some countries now that are implementing using molecular techniques for precision bioremediation on a regular basis. So it's definitely an exciting time, and I hope that you will consider this in your site management approach and really take the value that can be found from taking a holistic approach to site management and using these precision remediation practices as you're applying these great products and services. So I'll be glad to turn it over to Jack now so he can show you more of how these tools can be used.
Well, thank you, Dora. And I would say I'm excited and geeked out by that great summation of all the molecular biological tools that you went through. And I'll attempt in the last portion of the webinar here to take us into some practical examples in the field of how we utilize those tools in conjunction with a very popular amendment that Regenesis supplies. So for the rest of the webinar, we're going to talk about carbon-based sorption. I think everyone here that's a remediation practitioner would agree that this type of technology, this type of remediation amendment or product is very much in the toolbox. Sorption is not a new phenomena. We've understood that phenomena for many, many decades. But to incorporate sorption in conjunction with biodegradation, that's where the real action happens. And so from a standpoint of carbon sorption, using fine particles, just 1 or 2 microns in size, and being able to effectively distribute those in the subsurface as a remediation technology establishes a wonderful platform for sorption to occur and biodegradation to happen right on top of it. So as the process happens in the subsurface, when one of these products, one of these amendments is injected into the subsurface, you get a binding of the groundwater constituents onto these carbon particles, which reside fixed to the aquifer solids. Now, here's where the controversial aspect comes in. There are many people that want to argue out there that, well, I get the sorption part, but how does degradation really happen? You know, microbes can't get in all those pores. They can't connect up with the contaminants that are sorbed. Well, Dora said the magic word before, and that word is biofilm. A biofilm is what forms on the outer edges of those carbon particles. So as you have groundwater constituents that have sorbed to the carbon particles and the microbes start to enter the picture, you get this film that forms, this layer. And in that layer, there's a tremendous amount of interaction that occurs. Contaminants move in, contaminants move out, nutrients move in, nutrients move out. the microbiology moves in and out, and this dynamic biofilm is where that degradation takes place. So you can argue finite points about microbes can't, but I make the argument that microbes can. And there are lots and lots of papers now that document this phenomenon that's occurring. So yes, we get the sorption, but yes, biodegradation is an important part of this as well. And if you look at that simple graph that's on the top of the slide here, you can see that the yellow line in particular is a demonstration of this sorption and biodegradation phenomena as compared to the green line, which takes biodegradation out of the equation. And you can see the big difference between the amount of benzene that's been reduced or not reduced as a result of this sorption biodegradation phenomena. So this phenomena occurs much like on the biofilm that forms in the biotraps that Dora described. Same thing happens on the particles of these carbon-based sorption amendments. We're going to talk about three simple aspects in the rest of the webinar. Why Petrofix, which is the amendment featured today. How about the electron acceptors? Dora touched on electron acceptors and how important they are to the petroleum biodegradation process. And then we're going to have three quick hitter case studies, and I'll weave in how the molecular biological tools are used as part of those. So Petrofix itself is one of those carbon sorption-based amendments that is very much, for me now, a staple in my petroleum bioremediation projects. While historically I've thought about this product as suited to low to moderate mass scenarios, we've begun to push the envelope a little bit more into LNAPL scenarios and other high mass scenarios with some careful planning in advance. I love the fact that an amendment like Petrofix has the ability to be applied in grids or barriers, which I often do at the edges of a property or adjacent to a street. And then of course, within an excavation as an added amendment, because let's face it, if you have an open hole and you've removed a whole bunch of soil, chances are you didn't get everything. So to be able to place an amendment at that time, at the culmination of the excavation, I think is really important. And the way Petrofix operates, you use tight spacing and the filling of a certain percentage of the pore space in order to contact mass and also to manage mass flux as it occurs. When you have groundwater constituents that are sorbing onto soils and diffusing in and out of those soils, it's nice to have something in place that can manage that phenomenon and trap that contamination as it comes out of the soil particles. So why is this product useful for remediation practitioners? Let's think about it simply. It turns the subsurface into a filter so that the contaminants, as they move through the groundwater, contact these carbon particles, which we've established before are wonderful platforms for bioremediation to occur. And it's at that point where you get the locking in of those contaminants and the degradation of those contaminants, and you will see significant performant results over a period of time. I like this amendment as well because it's injected at low pressures. Very rarely do we see sites where we have to go much above 50 PSI. Most of the time we're in a 20 to 50 PSI range when we inject, and generally at low flows, under 5 gallons per minute. Amendment is infrastructure safe. I've already mentioned that it helps to manage back diffusion, and it's fast and persistent. You see results in a matter of months. For some sites, it could be as quick as 30 days. For other sites, it may take 90 to 120 days before you see that first significant result. And the other great part about the Petrofix amendment is that it has a nutrient package associated with it, or electron acceptors. And that's in the form of nitrate and sulfate, which are easily utilized electron acceptors that microbes really do use in the degradation process. And they're accustomed to using those constituents when they're present. So how about those electron acceptors? Well, let's get into that a little bit, because I think this is the other part, because sorption is great. And it's nice to be able to lock things in or hold groundwater constituents tightly to allow degradation to occur. When you add things like sulfate and nitrate to a site, you're going to see things happen. And there are numerous case histories out there in the marketplace of these electron acceptors being added individually with great performance results, because microbes will utilize these things to the hilt when they're provided in abundance. And we've seen nitrate used in many states around the country and Canada. And there's also experience in the EU, and particularly in countries like Italy and Germany and others, where you get very quick results if the regulatory environment will allow you to add those things. And the same is true with sulfate, because we find sulfate reducing bacteria ubiquitous across many sites. And these constituents are soluble. So it's not hard to get nitrate and sulfate dissolved in your injectate solution, get it into the ground, and have it distribute out into the subsurface. Another interesting thing about nitrate in particular is that it can be used by both anaerobic and aerobic bacteria, so it has great versatility. And sulfate, certainly when given in abundance, they're often very robust sulfate reducing populations of bacteria that are present on petroleum sites, and they just go gangbusters when they're given lots of sulfate. So these are the equations for nitrate reduction and sulfate reduction that we have here. Some people worry about adding sulfate, for example, that isn't hydrogen sulfide produced. And the answer to that is, well, theoretically that could happen if there is even a small amount of iron that's present. It helps offset and lock in that sulfide from becoming hydrogen sulfide, and in fact keeps that phenomena from occurring. So if there's iron present, you're able to knock down any hydrogen sulfide that might emerge. And there's lots of history out in the marketplace of using magnesium sulfate and calcium sulfate as amendments for remediation sites. And then we look at nitrate. The fear is always that we're going to generate a lot of nitrite. Again, something I rarely, if ever, see. And nitrite, if it did happen to form and accumulate, could inhibit microbial activity. But as we see in practice, even though something is possible theoretically, we see all these interactions in the subsurface that keep these negative adverse things from occurring. So let's get into the molecular biological tools, which Dora summarized so nicely. I don't have a Petrofix site that hasn't had use of these tools in some capacity to help demonstrate baseline conditions and then also show performance throughout the project. I mean, it could be simple as a bar graph that you see on the screen here that can show how changes manifest themselves in microbial populations or in degradation gene functions over time. And it becomes a great way to track performance in addition to contaminant concentrations or changes in geochemistry or changes in field parameters. And you know, Dora talked about the different molecular biological tools. I use Quantaray Petro the most because it allows me the most comprehensive look at all the different microbial populations and gene functions that I might see on a site. And I'll remind you that sites are not necessarily homogeneous in terms of microbial profiles. Many sites, in fact, virtually all sites, have a well network where there is diversity from well to well. The populations of microorganisms may look different at one well compared to the next, and the actual gene functions that are manifesting may look different from well to well. And it's nice to be able to have the analysis to track those. When I really need to prove degradation is occurring, I'll also blend in the stable isotope probing scenario that Dora had described earlier. And that's a nice way to show actual degradation and match it up versus the contaminant concentration results. So my preference, if I can, is to use biotraps on sites. Although for many of our sites, we've used bioflow filters as a quicker means of collecting samples for our microbial analysis. And if I do use a biotrap, we tend not to leave them in more than 45 days and probably more often just 30 days out in the field. If I have a site that's a bit more limited in terms of budget, then instead of the Quantaray Petro analysis, I'll use the qPCR, which has a limited number of targets that I might choose. For example, I might want to look at nitrate reducing bacteria and the gene functions associated with it. So I have a much smaller set of parameters that I'm looking at. So let's touch on these 3 case studies as we're get ready to wrap this webinar up. And I just want to show you different scenarios that are possible using the Petrofix amendment and then coupling in these wonderful tools that we have available to us. This particular case study is a fairly sizable excavation that was done. And if you look at the sidewall there and this very firm clay soil that exists, this is a excavation that was so-called painted with Petrofix. There are these little sand seams that exist at this site, and we get little trickles of groundwater that would seep out at very shallow depths. And by applying the Petrofix to the sidewalls of the excavation, we're able to capture any of those constituents that might squeeze out. And this type of an application was done with a sprayer, and we tried different ones till we finally got it right. And the base of the excavation was actually painted with Petrofix using a claw that picked up a drum of the Petrofix and actually went back and forth and spread it across the base of the excavation. So we used a couple of different techniques in order to apply this material to be able to lock in or trap any of these contaminants that might squeeze out post-excavation and keep them from migrating outside the excavation footprint. The site was about 2,000 square feet, the excavation area. As I mentioned, clayey soils with these very fine little sand seams. The excavation was dug right to the water table. And as a result of that, almost immediately when we hit the desired depth, we saw water that would percolate up. And having the Petrofix there allowed us to have the comfort that whatever's coming up from beneath that excavation was going to be sorbed at that time, and then the biodegradation process would continue. In this site, we had benzene concentrations over 16 milligrams per liter. And even outside the excavation, we had some minor constituents that were present and a target of 290 micrograms per liter for the application. We used 3,600 pounds of Petrofix. And again, this was a trial and error project. We tried different types of spraying devices and ultimately wound up with more of an industrial sprayer type setup that would allow the proper painting of the excavation. And because there were some oxygen release pellets readily available, we also put those into the excavation. So we applied oxygen pellets there as one electron acceptor, and then we also incorporated the nitrate and the sulfate as electron acceptors that came with the Petrofix amendment. So what we have within 19 months, we hit the target in the wells that were just outside the footprint of the excavation. We noticed an interesting phenomenon. This is something that we've seen from project to project. Nitrate and sulfate concentrations increasing at peripheral wells adjacent to excavations, often within about a 2-month period. So it's interesting to see that, and we would see that happen prior to actual degradation of the constituent that we were targeting. So it became sort of a signature we might expect at Petrofix sites. And because we use molecular biological tools, we always look for 2+ orders of magnitude changes in microbial populations and gene functions, and that's what we in fact saw in this particular case. So I think I've covered some of the highlights already. We had some interesting challenges with the spraying application, but we're able to solve those. We used this excavator technique or claw technique to paint the base of the excavation. And we did see these electron acceptors emerge up to 7 feet from the footprint of the excavation, which means they were getting through some of these sand seams and finding their way into the monitoring wells adjacent to the excavation. And this was the very first application of this type in the country. So moving on to case study 2, and this is absolutely one of my favorites because this shows you how you can use a variety of different tools to get the job done. I'm featuring just at this particular slide the Petrofix aspect of this project, but I'll talk a little bit more about the other aspects in a second. But Petrofix was used as a polishing amendment at this site after other gross removal mechanisms were put in place to treat this very contaminated site. So we had one Petrofix event with 23 gallons of injectate applied, a relatively small vertical interval of 5 to 11 feet below ground surface with 12-foot spacing on direct push injection points, 12 feet between rows, and 101 total injection points spread out over a series of areas at the site. And again, I mentioned this is a low pressure, low flow application. We averaged about 30 PSI and 4 gallons per minute for our injection processes at this site. And this is what the actual areas for Petrofix injection look like. The blue, the green, the pink actually was a tank cavity, the green area, and then a down gradient area in the orange, which is riddled with utilities. The interesting thing about the pink area is that Petrofix was applied at the very up gradient edge, right near the UST area concrete that was present there. And we actually used a vacuum on recovery wells that were staged on the down gradient side and pulled the Petrofix across the tank cavity and allowed it to disperse throughout that tank cavity and even emerge on the opposite side of the tank cavity. So while we weren't the very first ones to do this, we were amongst the first, and it became an interesting technique that now became available for other site applications. And you can see from the table that I'm showing here that you get a variety of different levels of performance depending on how well the Petrofix can be distributed within a given area. I call your attention in the middle to a well labeled MW7, and you'll see we only had a 13% reduction in our BTEX concentrations post-injection. And that was because in that area, we had difficulties getting our injection points in exactly where we needed them. So we didn't get the distribution and the pore space filled to the extent that we would have liked. Whereas take a look at some of the other wells, such as MW4 toward the top of the table, where we had substantial reductions in our BTEX concentrations because we got the right distribution. And we were able to verify that using core samples that we took to look at the vertical column and show that we nicely painted and distributed this Petrofix across the target vertical interval. So it's not uncommon, and I've done more than 60 of these projects with Petrofix now, to see these very stout reductions of 90% or greater for individual constituents like BTEX or naphthalene or TPH. And this is just another look at data from the MW4 well, which is just outside the tank cavity. And the yellow line is the total BTEX. And you can see post-injection, while you do get a little bit of fluctuation, that is characteristic of what you see post-Petrofix application, you'll see that the total concentration nicely trended downward, and to this day has flatlined at that site, at that location. So that's very much a signature of a post-Petrofix result. And the last case study here is just a very small injection grid at a site. Petrofix is ideal in amendment for these one-off wells or two wells on a site that might need just that little additional coaxing to get to a regulatory level. And at this site, a small service station site where USTs and dispensers leaked. And these were silty sand soils, so a little better permeability than some of the other sites that I worked on. We did have some clays that were interbedded. And again, we had some relatively stout concentrations at this well, over 10 milligrams per liter of GRO. And the average across the site was over 3 milligrams per liter. And our target level was 1 milligram per liter in the state of Washington. And so this was a 400 square foot area with a 10-foot injection interval and 400 pounds of Petrofix, or a little over 1,300 gallons of injectate were applied. And we used only 6 direct push points in order to target this little polishing area of the site. And this is right next to a street and a utility corridor that's just riddled with various lines. So a nice, safe, productive application that could be employed. So what did we see? Again, in a time frame of about 18 months, we're able to meet our criteria. And this site had been in remediation for greater than 9 years. And again, we saw nitrate and sulfate emerge. We were able to track our microbial concentrations and gene functions. And in this particular case, the regulators had a very keen interest in how we would monitor this type of a project, how we evaluate performance, because they wanted to use that as an example of how they could monitor other projects or oversee other projects of this nature in their state. So these are various applications for Petrofix and how we go about using different techniques and taking advantage of the molecular biological tools to show performance. And I'll just finish up my last slide here with saying that sometimes with Petrofix, you may have to use a gross mass removal technology in association. We used oxidation using an oxidant called Regenox, which is available from Regenesis. And we used high vacuum extraction on wells a few weeks after we applied the Regenox to the subsurface for gross mass removal. We pulled out lots and lots of contaminated mass through the detergent properties of the Regenox, through the solubilization of L-Napple on that one site that I had showed you where we did the extensive Petrofix application on the tail end of it. So that's a nice little technique to combine with Petrofix to achieve a result. And we use Petrofix as a polishing technology on many, many of the sites that we work on, just because we know we can rely on it and we have a monitoring program that we can count on, that we can track easily and understand when the process is working. And if we have to make any changes at all to it, we have the performance data available to do that. And the last thing I'll mention is that we also perfected a little bit of a UST flooding technique as part of using the Petrofix as another tool in our toolbox for petroleum hydrocarbon remediation. And with that, I want to thank everyone for their attention to Dora and I today. And I think it's time for us to go to question and answer.
Okay, thank you, Jack. Yes, we've now completed the formal presentation and we're moving into the Q&A portion of the webinar. Let's take a look. Yes, the first question here is for you, Jack. Are mass flux analyses helpful in planning Petrofix applications?
Thank you for your question, Amanda. The answer to that is yes. And it goes back to the fact that we're trying to employ as many tools in these remediation projects as we can. And mass flux meters of various types, whether it be for petroleum sites or for chlorinated solvent sites, are really great tools that help us understand Darcy velocity and mass flux in different zones within the subsurface. And they can be great to help us understand how to target our amendments and also how those amendments might move within the subsurface. If we have a very fast groundwater velocity, there may be a need to counteract that in some capacity. So having a mass flux tool or meter employed at a site is a wonderful idea, and I'd like to do it more often.
Okay, thanks, Jack. So here's another question. This one's for Dora. At what point in site assessment are molecular techniques most valuable?
Yeah, that's a great question. We can use them pretty much throughout all of site assessment. So if you think about when you get a new site and you're trying to understand what the microbial populations look like across the site, something like Quantum Petro that Jack was showing in his presentation is a great tool, because then you can see what the baseline looks like, how distributed these organisms are. And then when you go into your remediation phase and you add something like a Regenox product or you add Petrofix, you can do another round of monitoring of that Quantum Petro then to show that you've stimulated the right microorganisms and that you see an increase in either the aerobic or the anaerobic pathways that are happening for a variety of contaminants. And so particularly for petroleum hydrocarbons, I think that tool is useful. And then once you get to site closure, I think stable isotope probing is one of my favorite tools to be able to use, because you can show that the remediation of these compounds, biodegradation of these compounds is definitively happening at that point.
Okay, thank you. Let's have a look. Jack, another one for you here. Do you collect soil cores at every Petrofix site to demonstrate distribution of the amendment?
I would say in as many sites as I can. It's not always feasible to collect soil cores, but if I have the opportunity to, I do it because it just instills that extra confidence that you've got the proper distribution. I would say that in every pilot test we do with a product like Petrofix, we always do soil cores associated with that. And then it varies at full scale depending upon timing and budget.
Okay, thank you. The next question, Dora, maybe you can take this one. What lines of evidence are most important for petroleum hydrocarbon site assessment?
So I think if you want to do a really well-rounded job of site assessment, looking at the standard parameters in the chemical assessment, looking at the geochemical parameters, adding in the microbiology like the Quantaray Petro, but then also some of these very innovative tools like the flux measurements can add a lot of value. So I think overall taking a multiple lines of evidence approach so that you understand the hydrogeology of the site, you understand the microbial populations, you understand the chemistry and the geochemistry is what's going to give you the best information to be able to do good remedial practices.
Okay, thank you, Dora. So another question, and this is from someone who's used Petrofix before, I think. Jack, can you take this one? How do you address obvious Petrofix presence in monitoring wells post-injection?
That's a great question and something that we deal with on a regular basis. I mean, it's not bad at all to see Petrofix find its way into and through a monitoring well. And you'll see various differences in color from very black to gray-like in nature. It's nice that Regenesis supplies a little test kit that allows one to look at the potential concentration of Petrofix in a well, or to be able to take a VOA vial and try to look through it with a sample from the well. And if you can see through it, chances are you can sample that well. But if you should run into a situation where there's too high a concentration of Petrofix, or you can't see through that VOA vial, then you're going to employ some additional techniques, which could include flushing out that well with several water flushes. That might also mean filtering that well. Could also mean there's a nice little alum kit now that you can use to drop out the Petrofix and actually get a clear sample. So there are some techniques that can be employed. Back in time, there was talk about using passive diffusion bags. And I think the general consensus now is to move away from that because there's a potential for Petrofix to get into the diffusion bags. So while that may have been on the table a long time ago, learning has told us that that's not one of the options. But we have all these other great options to help us get a true representative sample.
Great, thanks, Jack. Right, I think we have time for one more question, one for Dora. Are microbes adversely affected by the absorption to Petrofix?
Actually, I think it's the opposite. From what we've seen in all the case studies that we've looked at, post a Petrofix application, you typically see very good stimulation of microbial populations. And I think that's for a couple of reasons. I think you have microbes that like to be in biofilms, and so they start to attach to these particles, and these particles have absorbed these contaminants, and so they're readily bioavailable for the microorganisms, so it fuels their growth. You see a lot of stimulation. So I think post application of Petrofix, we have really good response where you'll see 1 to 2 orders of magnitude increase in the microbial community.
Okay, thank you, Dora. Yes, so this is the end of our chat questions now. If we did not answer yours, don't worry, somebody will be following up with you via email within the next couple of days. If you'd like to learn more, feel free to get in touch directly with Jack or Dora. And if you'd like to learn more about the remediation technologies from Regenesis, please visit regenesis.com/EUR, which will take you straight to the European website. Now, thank you very much again to our presenters. And thank you to all of you who joined us today. Have a great day. Bye-bye.